Okay, so today we're going to talk about pH, which you've probably heard of. pH is a way to quantify how acidic or basic a solution is. So pH is defined as the negative log of the concentration of hydronium ion. And this is a base 10 log. You'll want to be sure on your calculator that you don't get it confused with the natural log, usually abbreviated LN. And the advantage of using a logarithmic scale in this way is that a very wide range in H3O plus concentrations is sort of condensed down to a small range of convenient numbers to use. So if I have, say, H3O plus concentration and pH. Okay, if I use round numbers, then this is really easy. If I have something like 10 to the negative 7th, then the pH would be 7. That is a neutral solution. If I have 10 to the negative 12th, then the pH is going to be 12. If I have 10 to the negative 2nd, then the pH is going to be 2. And so you see these, are different from each other by billions. It's many orders of magnitude difference, and they're all condensed down into some simple numbers. pH of solutions can technically extend into the negative numbers and above the number 14, but those are only exceptionally highly concentrated acidic and basic solutions. Generally speaking, a range of 0 to 14 is going to cover almost every solution you encounter. So a pH of 7 is neutral, a pH greater than 7 is basic, and a pH of less than 7 is acidic. If we know the pH and we want to find the H3O plus concentration, then we just need to undo this log. So the first thing to do is to move that negative over to the other side. So negative pH is equal to the positive log of the hydronium concentration. And then to undo the log, we raise 10 to that power. And so 10 raised to the power of the log of H3O plus is simply the concentration of H3O plus. The concentration of H3O plus then is equal to 10 raised to the negative power of the pH. So we'll do some practical examples with this later, but I just want you to be comfortable with going from H3O plus to pH by taking the negative log, or going from pH to H3O plus by taking 10 raised to the negative pH power. And again, on your calculator, make sure you know where the log button is, and make sure you know where the 10 raised to the negative pH power is. We can also define the pOH, and that's the negative log of the OH minus concentration. So in terms of pOH, a pOH of 7 is neutral, just like the pH of 7 is neutral. But then a lower pOH would actually be basic, and a higher pOH would be acidic. Now if I take that Kw, that's 10 to the negative 14th, and that is equal to the H3O plus concentration times the OH minus concentration. If I just take the log of both sides here, if I take the negative log of both sides here, then what I'm going to get is that 14 is equal to the pH plus the pOH. So our Kw expression relates the H3O plus and OH minus concentrations, and then here we can just relate the pH and the pOH directly. And what this does is it gives us a really convenient way to interconvert between all of these numbers for acid-base solutions. So if I have H3O plus here, and pH here, I can convert from H3O plus to pH by pH is equal to the negative log of the H3O plus concentration. I can convert from pH to H3O plus by H3O plus is equal to 10 raised to the power of the negative pH. I can have the OH minus concentration and the POH, and they have a similar relationship. OH minus concentration can give me the POH because the POH is the negative log of the OH minus concentration, and I can find the OH minus concentration by taking 10 to the negative power of the POH. So that would be going the other direction. But I can also go back and forth between pH and POH by using 14 is equal to the sum of the pH and the POH. And I can go back and forth between H3O plus and OH minus because 10 to the negative 14th, or in other words Kw, is equal to the product of H3O plus and OH minus. And so you see, if you're given any one of these four quantities, you can calculate all the others. Let's take one that's maybe not as common, the POH. And I'll just pick a random number. So if the POH is 3.27, can we figure out all of our other quantities? Well, the pH is related to the POH according to this equation. So I'll just take 14 minus 3.27. And I get a pH of 10.73. And I'll circle these so they stand out a little bit. Okay, and if I want to find the H3O plus concentration, then I'll take 10 raised to the negative 10.73. So that's 10 raised to the negative 10.73. And my H3O plus concentration is 1.8 times 10 to the negative 11th molar. And if I wanted to find my OH, then I would take 10 to the negative POH, 10 to the negative 32.7. Sorry, 3.27. Oops, forgot the negative. There it goes. Okay, and I get OH minus concentration of 5.37 times 10 to the negative 4th molar. And we can double check that everything worked properly by taking the product of these two and seeing what they equal. And wouldn't you know it, they equal 1 times 10 to the negative 14th. And so this is, I think, just a really convenient way to summarize all the sorts of calculations that you might need to do with pH, POH, H3O plus concentration, and OH minus concentration. How do you actually go about finding these numbers, though, in a laboratory setting? So there are a number of different ways you can determine the acidity in a laboratory setting. We're going to look at some figures to show that. So the first is with color indicator. This is an example of what's called universal indicator, and it's a solution where you put just a couple of drops in your of universal indicator into your acid-base solution, and it will change the color of the solution, and based on the color you can tell the pH. And so if you have, say, a bright yellow solution, then you know the pH is something between 5 and 6, and your H3O plus concentration then is about 10 to the negative fifth, or maybe 10 to the negative sixth. So that's called a universal indicator, and it's a solution. You drop it in, just a few drops in your solution. You can also use pH indicator paper. So sometimes it's called litmus paper. And this is just paper that's actually been soaked with universal indicator and then dried out. And so you can put a couple of drops of your solution onto this paper, and the paper will change color. There we see a kind of a green color for their solution, and so the pH is 8. So the H3O plus concentration is 10 to the negative 8th. The OH minus concentration will be 10 to the negative 6th. And so I want to just tell a little bit about how these indicator solutions work. Color indicators are actually acid-base conjugate pairs. And so there would be the acid and the base, and they are a conjugate pair. And what's special about them is that the acid and the base both have a color, and they're different colors. So sometimes you'll have one where the acid is yellow and the base is blue. So that's what bromocresol blue indicator is like. And what you do is you add the indicator in such a small concentration that it doesn't control the pH, instead it responds to the pH. And so whatever acid or base solution you're dealing with is going to have a pH that's controlled by the primary acid or base that you've added to it. And then you just put a minuscule amount of this indicator in solution, and it will, under acidic conditions, it will be yellow. And under basic conditions, it will be blue. And then actually, somewhere in the middle, it would be green. And then what universal indicator does is it takes a number of these individual indicators that are all nicely tuned. They're selected such that you get a really distinct different color at every pH number. And so that is how indicators work. Now there is one other way to measure the pH. And here it is with a pH probe. So this is an electrochemical probe. You put it in your solution and it will actually produce a voltage. And how it works is pretty interesting, but we're not going to get into that. All you need to know is that the voltage will depend on the pH. And so you have a little meter there that's going to read the voltage and convert it to a pH for you and display it in nice big numbers for you. So this solution looks like it's 9.11 pH. And so a pH probe is usually very fast to respond, and so they're useful to use if you're trying to monitor the pH over the course of a reaction. Of course, it's digitally collected data, so you could save that information to a file and work with it on a computer spreadsheet later on. And so pH probes are really convenient, but they're also big and bulky, and you need to plug them in and set them up, and oftentimes a color indicator is sufficient and a whole lot easier, and so we'll just use the color indicator instead of the pH probe. And I think I'll pause this and we'll do another section in just a second.